I'm Kirk Harnack. On This Week in Radio Tech, I'm joined by Chris Tobin and Chris Tarr. We're talking about RF interference and how to keep it out of audio circuits, how to fix it. On This Week in Radio Tech, next.
Netcasts you love.
From people you trust.
This is TWiRT.
Bandwidth for This Week in Radio Tech is brought to you by CacheFly at CacheFly.com.
This is This Week in Radio Tech, episode 107, recorded November 16th, 2011. You're grounded. This Week in Radio Tech is brought to you by Axia Audio and the new Radius IP audio console. Feature-rich, affordable IP audio consoles from Axia. On the web at axiaaudio.com. It's time for This Week in Radio Tech. Hi there, I'm Kirk Harnack, your host for the show. Thanks for joining us. It is this show, this podcast, this netcast, where we talk about really geeky things about radio and radio broadcasting and audio and transmitters and getting, audio signal out to literally millions of people every day. And that's what the radio industry in the U.S. and all around the world does. And it's becoming more than signals over transmitters and over the air. It's, it's becoming a big source of content on the internet, whether it's sports or talk or more music services. The radio is really in the content creation business. And it's the engineers behind the scenes that help make that happen. I've got two of the best engineers right here with me on the show. Let's first introduce from Manhattan, New York City. It's the best dressed engineer in radio. Well, maybe not this episode. It's Chris Tobin. Hey, Chris.
Hello, Kirk. I'm trying my best to. I can't outdo you tonight. You're in that undisclosed location, TV
right.
studio, high definition.
Tell us a little bit about Chris Tobin and why are you qualified to talk to us about broadcast engineering and the geeky stuff we'll talk about on this show.
Well, let's see. I've been doing it for about 20 years plus. I've done work with local radio stations, 2 radio networks, 4 different network newsrooms, and multiple satellite earth stations and transmitter facilities, both AM and FM, and have done some television. And now currently I'm running president of CCS Music Cam, and we manufacture audio and video codecs for broadcasters, both in television and radio and other places. So things have been good. It's I got a lot going on in the background.
Also on the show is our other co-host, and that is Chris Tarr from Mukwonago, Wisconsin. Hey, Chris.
I am not in an undisclosed location. I am in my bedroom with the frog over here. I'm the director of engineering for Intercom's radio stations in Madison and Milwaukee. I'm also a contributing writer to Radio Guide magazine. I also run the website Virtual Engineer at broadcastengineering.info and many, 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 many other things.
Okay. So many that your wife probably says, Chris, are you going to keep doing all those things? You're going to come home tonight. I
seem to recognize her. I think when I see her walking down the street, I know who she is. I just don't see her that often, so I'm not sure.
All right. Hey, well, let's get right into our show, which is brought to you by axiaaudio.com. And you're welcome to check out their website. That is my employer, the folks at Telos, Omnia, and Axia. And I appreciate very much their sponsorship. And I and they would appreciate your going to the website and check them out. I'll tell you a little bit more about Axia and some of the consoles that Axia makes that Leo uses a little bit later on in the show. Here's the subject for this program. It's about the best wiring practices for analog or digital or any kind of wiring when you are dealing with a high RF environment. What does that mean? Well, let's say that you're a radio station and you have a transmitter right there on site. That transmitter is putting out a lot of power probably and putting a lot of RF into those wires. If maybe you have occasional RF, like I was just at a radio station this week in Nashville at the studios where they have 2 high-power transmitters on site, but they're for backup. So they're not used all the time. In fact, the idea is to never use them. But when they do fire them up, how do you know that the wiring changes you may have made or added over the last little bit are still good? So, Chris Tarr, I'm going to let you take it away at this point and kind of set things up a bit more and get right into the subject while they do a little live tease here in the studio.
Fantastic. Well, RF in studios, it happens all the time. We work near transmitters very often, either in the studio or also at the transmitter site. It's everywhere. And especially if you have an AM, you know the noise. You pick up the phone and there's your AM station talking right back to you over the phone. So what we're going to talk about for a little bit this evening is how we combat that. Now, I'm sure, Chris, you've probably run into this many, many, many times in your exploits where you're working in a studio and you're wiring something up and all of a sudden you're hearing the radio station.
Oh, absolutely. Let me see. How many AM sites have I done that at? Oh, actually, it was an FM site as well. Yeah, I've long wire antennas inside the racks have worked really well to pick up the sounds.
Things that people talk about or even forget to talk about sometimes is that things like phone lines, audio wiring, all make really great, excellent AM radio antennas. We all have it with toasters and picking up answering machines and things like that. So what we're going to talk about are some of the things we can do to alleviate that problem, to kind of get rid of the RF in your plant. And I guess first off, the most important thing we need to talk about is grounding. What are some good grounding tips? You can do anything from, grounding the entire building to grounding racks. There's a whole gamut of different things you can do. So I guess that's first thing we'll talk about. I think we're going to have Tobin come back here in just a second. They're getting him reset. Well, one of the things we can talk about here with building grounding is think of things like Faraday cages. For example, the facility that I have is right at an AM transmitter site, which is not unusual. A lot of radio studios still, especially AM stations, are still co-located at their transmitter site. So in the example that we have here, we have a lot of copper in the walls, effectively screening around the building, which takes care of any kind of RF entering the building. All of that copper screening drains to ground. So that's the first step. I think, Chris, you've run into things like this too, where a lot of times almost all of your problems can be figured out just by grounding practices.
Oh, absolutely, absolutely. One of my transmitter sites. Let's see, we had phones. We installed some phones, and the old phones we had we'll call them Bell system phones. Those real good old clunkers, and we had to change them out. And as a result, we went to some newer phones that didn't have the same RFI protection, if you will, radio interference filtering and whatnot. And it was interesting. You got all kinds of music and stuff on the phones, even when you aren't on hold. But we found that there was a point on the circuit board that if we grounded that one spot to the strap of the ground system in the building, all of the interfering music on hold just went away. It was the wildest thing. Lift the wire off that spot, came right back. Go to other places on the circuit board on that particular phone, didn't matter. Just one location. so grounding is a little experimentation as well.
Well, I think that's really the first thing you need to do is before you start anything else, make sure that your plant is grounded. Because if there's any break in that ground anywhere, it doesn't matter where you're going to go, you're going to have those problems. For example, I ran and it doesn't even, you don't even have to be right on the site. For example, we one of the stations was at AM station. We had a phone call from a woman who was hearing the radio station on her phone. Went down to check it out, and there was no ground on her phone system coming in, the phone lines. They didn't have a modern demarc point. It was an older house, and it had the phone wires coming right into a ceramic block and off to her telephone. So phone wiring especially makes a great antenna at AM frequencies. So, really the first step is making sure that you've got your building ground done right. And a lot of stuff falls into place after that, because then it's just a matter of tying things into your station ground. I know, Kirk, we were talking about this earlier, and you brought it up. You've done some projects too where you've run into that, and it seems to me like a lot of times you run into older facilities have this problem more often, either because they weren't grounded properly in the first place, or they're so old that over time, ground straps or things like that tend to break or disappear.
Hey, can you guys hear me? Am I back with you? Okay,
yep.
Good. Hey, well, I thought actually that, if you don't mind, I want to actually step backwards a little bit in the conversation and define the problem just a little bit more. So then when we talk about what the solutions are, it would make more sense to those who in the audience who haven't actually experienced these problems before. We mentioned earlier about, okay, you have a high-power transmitter on site, either an AM transmitter or an FM transmitter that's close to the studio, close to where you have a lot of wiring, and not just wiring, but you have a lot of audio devices. And if you think about the world of analog analog audio devices, okay, you've got an audio console or a CD player or whatever other devices you may be using that have analog outputs and analog inputs. And so these, then you have wire connecting these things. In some cases, the wire is pretty short. You've got a CD player next to an audio console, and the wire may be 2 or 3 feet long or 6 feet long or so. But in other cases, you've got a lot of this in typical radio stations, a lot of long wires that go from one studio to a central rack area. Or from the central rack area to a studio, or from one studio to another studio. I mean, here at the TV station that I'm at right now, there's miles of wiring in the floors, in the ceilings, in cable conduits and stuff. All this wire, as you guys alluded to earlier, can act like antennas. It works. Some signals are easier to pick up than others. But okay, so what? So what if a wire acts like an antenna? I mean, I can hold a piece of wire in my hand here, and sure, it's picking up everything from Russian satellites to cell phone signals to a radio station transmitter a mile away. It's not hooked to a radio. It's picking this stuff up. What's the problem with wires in radio facilities where there's audio equipment? Well, the problem is when perhaps the input to an audio device, like an input to an audio console, becomes overwhelmed with a high amount of radio frequency RF signal that's on that wire. That's probably one of the most common things. Then there's also the problem of an audio input, which in professional applications are typically balanced inputs. So the audio amplifier on an input is looking for what is the difference between this wire and that wire, the plus wire and the minus wire, as we typically call them. And it only amplifies the difference in those two things and calls that audio. And typically RF coming in on a wire is not a differential signal. It's a common mode signal. It's equally on both the plus and the minus wire. Then there's also the problem, though, of RF getting onto the what we like to call ground of a console or the ground of a piece of equipment, a cassette tape machine or a CD player or an automation, an audio card on a computer. So if there's a lot of if ground isn't really ground, if ground is really containing a lot of radio frequency energy, then this can cause problems in and of itself if ground isn't really ground anymore, if there's a lot of signal there of some kind. So those are some of the ways that RF gets onto wires. Now, what problems does that cause? Well, as I mentioned earlier, if you have a very much an analog radio station or audio plant, then you could be very likely to demodulate this RF. If it's an AM signal, well, that's relatively easy to demodulate. All it takes there is a diode connection, two dissimilar metals, steel and brass together, for example, can act to demodulate that audio. And once that audio is demodulated, well, then any audio circuits that it's connected to, they don't know the difference if it's intended audio or unintended audio. If it's demodulated, it's audio. It's traveling along the same wire as the desired audio. Then there's the problem that we come into with FM. FM certainly is, I guess, a bit more difficult to demodulate because it's frequency modulated. So just a dissimilar metal connection won't demodulate it. But a lot of times, if we have an on-site FM transmitter, we're very close to the transmitter, and most any FM transmitter will have a certain amount of what we call AM synchronous noise. So the FM transmitter is behaving a little bit like an AM transmitter as it sweeps frequency up and down and doing its frequency modulation. And that AM synchronous noise basically becomes a 100 megahertz AM radio station that then gets impressed upon all the wiring in the station. That ground isn't effectively taken care of. So those are a couple of ways that RF can get into things. With TV stations, you get strong RF onto cables, and you can end up with bad-looking bars and wiggling in the TV signal. Now, the digital era has improved a lot of this and made a lot of equipment less susceptible to RF interference that you'd be able to hear. Not necessarily impervious, but a lot less susceptible to it. So anyway, let's get back to the to the analog portion now, because I've always found that analog circuitry, analog equipment is the most difficult place to get RF out of. And hey, a lot of us have had a stereo system at home, and we might live within half a mile or a mile of some transmitter site, and you get the radio station in your stereo system, or you've taken a call from a listener who says your radio station comes in my telephone. Well, because the phone company has all these antennas all around your city. They're called phone lines. So okay, I've kind of set the stage a bit for what the problem is. RF getting impressed upon wiring, and in most cases, the problem comes about with analog connections, analog wiring, like microphones, or like even headphones. We can't be digital everywhere. Microphones are inherently analog devices. Our voices are, and headphones have analog connections to their amplifiers, and RF can get into those analog connections. So now that I've kind of set that all up, I'm sorry, Chris, why don't you go back to addressing some of what I was saying, and go on with your own, and tell us how these solutions you were talking about, like Faraday cage and shielding and good grounding, what do those things do to reduce or eliminate the problems that I set up for us?
Well, essentially the copper and the Faraday cage effectively block those signals from getting into your building and getting onto the wires in the first place. So, if you're talking about a transmitter plant, that's generally, in terms of best practices, that's the first thing you do. And it may not be the entire building. It may be parts of the building where you just have wiring, but that's the first line of defense. Generally, you take care of that, you're in pretty good shape. And what happens is the RF is essentially soaked up by the copper Faraday screen and grounded out into the ground and stays away from your wiring. Now, after that, you may still have some stuff coming in, and this also goes
Chris,
for.
Hey, yeah, I've got a great analogy here to explain to folks how a Faraday cage works. Okay, so I am the electronic circuits that are desired to be working, right? Okay. You are the RF. Now we're going to demonstrate how a Faraday cage works. Go right ahead, Chris.
Yeah, see, I'm talking. Kirk's not hearing me. That's because he's covering his ears with a Faraday cage. For an example, to show how effective these are, in my building, try walking around with a cell phone inside my studios. Good luck. I have a real hard time keeping a signal unless you're near a window, because effectively any kind of RF trying to get into the building is blocked at the wall. But you are going to have some stuff creeping in. Either you don't have that screening, or possibly you can't afford all that copper in a building, or you're in an older building where that's not the case. Then you have to resort to some other measures, which is getting the RF off of the copper once it's been on there. And Chris was kind of alluding to this earlier, things such as, chokes and torides. So I know, Chris, you've got some examples of some of the things that you can do to keep the RF off of the wires. And effectively, we're doing what? We're attenuating the RF. We're blocking the RF on some of these wires. Oh, can't hear you.
No audio from Mr. Tope.
There we go.
Oh, there we go.
It's a combination of, let's see, you're attenuating the RF signal, you're absorbing the RF signal away from the device that's being affected in a bad way, or you're accepting the fact that the RF is on the wires, but because of the physics of, say, twisted pair wires and the difference between balanced and unbalanced connections, you actually can cancel out any of the interference that would be common to both the high and low side of the wires. So depending on the need, the application, yes, you could be attenuating, accepting it, and canceling it out. There's a couple of ways to do it. But toroid cores, or the little ferrite beads, as they're known as, they're made of iron ore, and at different sizes and frequencies, they can be used to attenuate the interference that you're getting from your AM, FM, or TV, or even two-way radio stuff.
Let me point out a quick example here of a ferrite core, guys. I'm gonna grab my camera here and move it just a bit, and point it here at one of the USB cables coming out of my computer. That lump in the camera cable is a ferrite core. Now, why would there be a ferrite core on a USB cable going to a webcam?
Oh, it's the clocking signals from the microprocessors, the digital circuits, they actually operate at RF frequencies. You know, did you ever let's see, the ferrite, the USBs are running at what, 700 megahertz? That's an RF frequency. Your CPU operates up to what, 2 gigahertz? It actually creates an RF signal. So there's a few things that go on.
So that core is there, and it's on. You've not probably noticed it's on a lot of computer cables, a lot of video cables for computers, and other cables have that lump in there, and it's there to help the. Generally speaking, it's there to help keep signals in the computer from emanating out common mode on that cable. I wouldn't think it's actually there to keep interference from coming into the computer. It's more to help the computer and the cable as a set meet RFI emission standards, so that if you were
Absolutely.
because that cable, that USB cable, can act like an antenna. And ground in the computer isn't necessarily just a fabulous ground. I mean, I know that with this Mac right here. I never can understand grounding of a Mac. The metal case will tend to shock you if I'm in Europe and it's plugged into 240 volts. I can always feel a little bit of something there on the unit itself. But my point is, well, the laptop isn't tied to a radio station, ground bus bar. So indeed. Let's continue to cover toroids and chokes. So a toroid stops, I guess, what you'd call common mode RF movement, right? So you have a cable. Typically, you have a cable that might have 2 or more conductors in it, and it might even have a shielding around those conductors. But then we take those conductors and we wrap them. Either we clamp a toroid on it, or we wrap it through a toroid. This is commonly done in radio stations when you got a bad RF problem. And by wrapping this whole thing through the toroid, one or hopefully several times, we're allowing the differential mode signals to continue. They don't know. The differential mode signal, that is, plus and minus, changing phase relative to each other and changing voltage relative to each other, they don't know they're going through a toroid. They don't care. They just, they might, think, hey, why am I going around in circles? But they don't know they're going through a toroid. It's the outer part. It's the common mode. It's both wires carrying the same signal in the same phase together. Common mode that would realize, oh, I'm going through a toroid. I don't want to go through a toroid because I have to give up a little bit of energy every time I go through the toroid. And so a toroid stops this common mode RF signal. Am I kind of right on that?
Yeah, pretty much. Yeah, well, and common mode signals is actually the most common RF problem that we deal with in broadcast, and in fact at home that's probably a lot of the RF that you're dealing with at home is the same kind of thing. A great example is in my car, I had a charger that would put a lot of noise on my car adapter for my iPod. So what did I do? I took it, wrapped it around a toroid a few times, boom, gone. So same thing with phone line noise. Essentially what you're doing is you're buying a toroid to put along your phone line to eliminate AM broadcast noise. So you'll find that a lot of what you're dealing with in broadcast and even at home is common mode, and you'll most of the time deal with toroids. Now keep in mind, when you're looking at toroids and you're looking at ordering toroids, they have different mixtures of the ferrite and iron and that sort of thing, and they work at different frequencies. They cancel out different frequencies. So you'll buy a different mix of a toroid for AM frequencies than you would for, say, FM frequencies. So be sure to do your research when you buy toroids. But I mean, I don't know about you guys, but that's the most common type of interference that I deal with in terms of RF in my facilities.
Yeah, that would be true. That I've had that.
Well, one thing I sure noticed is some years ago, gosh, it's been a long time ago, I've bought a couple of, or been involved with installing a couple of Nautel brand transmitters. And Nautel was always, I thought, pretty good about it, including some accessories that you would need to install the transmitter. And one of the accessories that they tended to include are a certain number of toroidal chokes. So I've received some that were kind of large, and the instruction manual says, hey, run your AC power cord through this a few times and then plug it into the back of this exciter or this transmitter. Or when you run 220 volts or whatever into the transmitter, run the, take all of them and run them through this toroid a few times and then connect them to the AC power input. Hey, when you bring the RF coax into the transmitter, what's going to take the high power out of the transmitter, run it through this toroid. You're not going to be able to loop it, but put it through there once. When you bring your audio connections from your audio processor over in the next rack, run it through this smaller toroid a few times and then connect it to the audio input on the transmitter. Now, why are they wanting every input and output on the transmitter to go through a toroid first?
Well, that's for high voltage most of the time. That's for things like lightning and that sort of thing, where you want because of skin effect, and essentially you want that current to be basically to saturate the core of the toroid and take it off of whatever's inside. So we see that a lot. Plus, there are some situations where get RF into things like exciters. Cause a lot of problems. A great example is I had to have an FM co-located with my AM here in Milwaukee. And I would say a couple of years ago, I get a phone call from a friend of mine who said, you want to check something out? I'm listening to you. A couple channels up, I'm hearing a combination of your FM signal and your AM signal. So, I take a look and sure enough, about 1.25 megahertz up and down, I'm hearing a combination of both stations. Well, my AM station is 1250 kilohertz. I was getting into wiring going to the FM exciter. The FM exciter was taking that signal, modulating it, sending it out. So we had this combination of signals, 1.25 megahertz up and down. So the way you fix that is you put some toroids around that and took the AM component going into that FM exciter. So that's why they have, Nautel is great about packing toroids by the bagful when they sell a transmitter. And you're right, they instruct you to put them on everything.
So toroids are one way to take care of this, and we understand that toroids will help stop RF, which is common mode, which is the most typical way that this is happening. But I've also seen another technique where we use some kind of capacitors. Typically, maybe you have an input to an audio console, and you're getting some RF when you bring up that source on the audio console. You're hearing some demodulated RF. I understand that you can take a small value capacitor and go from each side of that audio feed, the plus and the minus, to a common ground. So when we put a capacitor there, what's happening? Mr. Tobin, why don't you take this question? What's happening with this capacitor? Does this affect the audio? And is this effective at reducing the amount of RF going into a circuit where it doesn't belong?
Well, it reduces the amount of RF getting into the circuit. The capacitor arrangement you're talking about, commonly known as a bypass capacitor, it's a low value, typically as like 0.01 microfarads. And the idea behind it is that it just bypasses. So it's diverting the RF interference, you call it, to the chassis, to the ground, wherever you have the bypass capacitor. If properly done, the audio should not be impacted because it should pass the audio frequencies, but anything above audio frequencies like the RF signal, it'll bypass. That's basically what it does. It becomes a block at the frequencies. The capacitor's value just blocks the radio frequencies and bypasses to chassis, or we'll call it chassis ground.
And by the way, those bypass capacitors, we also use those on things, for example, like tower light flashers, when there's RF getting into those as well.
Oh my goodness, that's right. There's a prime example of a really sticky situation. Here you've got, let's say, an AM tower, and it's got to have lights on it, right, if it's tall enough. So you've got this tower light flasher. Well, now the old ones were mechanical, and they weren't very, susceptible to RF problems. There was a motor and a rocker and a mercury switch that went, and okay, that's fine. But nowadays, we use solid state flashers. So you got this module that's potted, and it's got a flasher circuit in there. It's typically got 3 terminals on there. So there's one for the AC 110 volt neutral, and there's one for the source, the hot, and then there's another lead that gets flashed. And so the tower lights are hooked to the neutral and the flashed, and the incoming is hooked to the neutral and the hot. Well, this thing is supposed to be mounted on the tower, typically in a box, and oftentimes there's a photocell right there too that runs a relay and turns the whole contraption on and off. But so you've got all this AC wire going up the tower, and it's going to have plenty of RF on it. Now, typically it's in conduit, but still it has a lot of RF on it. And this RF can screw with the operation of the solid-state tower flasher. It cares. It's got electronic parts in there. So you're saying that oftentimes you'll see some capacitors. I've seen these capacitors. In fact, I've seen them blown up. when lightning hit or there's a power surge, and these capacitors go from an AC line to ground to the or to the tower itself, to some way to get the differential gone so that there's no RF differential between ground and or the tower itself and the AC.
Yeah, and what you'll see is if you don't do that, you'll have things like tower lights that are blinking with the modulation, or they'll start to blink until the audio goes silent and then shut off. And I actually had that situation first time we put in solid-state flashers, where whenever it was a great silent sensor, because whenever there was no audio, tower lights would stop blinking. So
I worked at a disco station, and that was perfectly acceptable for the lights to flash with the music. Yeah. So there's one more technique I want to talk about. So we've talked about chokes and capacitors a bit. And you can choose the right, and there's formulas, you can figure this out. You can choose a capacitor that will have no effect on the audio frequencies, not even the highest audio frequencies, but it will shunt a great deal of the RF to grounds. The capacitor, is like a frequency-dependent circuit. And part of the frequency dependency here, we're talking about the input impedance of the circuit and just the apparent impedance that's going on right there, and some of that may be variable. So different value capacitors. We're talking about small capacitors, by the way. Several picofarads or 0.001 microfarads. We're not talking about power supply capacitors here. We're talking about small, typically mica capacitors to do RF bypassing. But another technique is to use a choke that is in series with the audio. So a choke would be a wire wound typically around some kind of a core. It may be an air core, or it may be actually some kind of a ferrous core. But the idea here is that a choke would, a choke passes DC just fine. But as the frequency gets higher, the choke impedes the flow of electrons, or the flow of signal through it, depending on the value of the choke. So you would choose a choke, and typically these are reasonably small, that would present an impedance to RF, but not an impedance to audio. Now you combine the choke and the capacitor in the right way, and then you have an LC circuit. You have an inductance and a capacitance circuit, which can be very effective at being selective. That's what we're looking for here. We're wanting to pass analog audio and yet selectively get rid of anything that is higher than the audio frequency, that would be RF, and shunt that to ground. And an LC circuit would do that. Chris Tobin, do you have experience in either designing or sizing these kind of parts so that they're pretty effective at getting rid of RF?
I haven't done it in a while, but yeah, there are formulas that you can use. Most equipment today really handles RF very, very well. Some of the chokes back in the day, you had them in power supplies for some of the transmitters, and you had to sit and sort of do the formula for an LC network and cut the wires out, reduce some of the coil. But for the most part nowadays, everything is pretty solid. I don't know. Let me see. I haven't had many instances or needs to build an RC or an LC network at all for shunting RFI.
Isn't it kind of interesting that here, the three of us engineers in this era where we've had a lot of digital in the last few years, AES digital and now IP audio over Ethernet digital, we're finding that there's a lot less need to know these techniques to get RF out of stuff. There still are occasions where we have to do it. And tell you what, after a commercial break from our sponsor, we'll get into that a bit, and then we're going to return to the subject of grounding and grounding technique for lightning protection and for keeping RF out of stuff. Right now, I want to take a break and tell you about our sponsor. It's also my employer, and I'm really glad to have them on board as a sponsor. It's Axia Audio. Axia, the inventor of LiveWire, which is the low latency, basically unbuffered, uncompressed way to pass beautiful mono, stereo, or even surround audio over Ethernet IP, standard off-the-shelf Cisco, HP switches and so forth. And the low buffering, the low latency also makes it perfectly usable on the air. One of the challenges to come up to fix about putting audio over Ethernet IP is that if you use standards that existed prior, like CobraNet or EtherSound, these are perfectly good standards, but they don't really pay much attention to the problem of latency. So when you talk into a microphone, when a disc jockey talks into a microphone, and this audio is converted to digital and converted to IP packets, it flies around the network, it gets mixed in a mixer, and then it comes back out through some interface to a disc jockey's headphones. If there's more than about 3 or 4 milliseconds of latency there, it sounds weird to the disc jockey. So you've got to have a way to keep the latency very, very low. Well, with LiveWire, that's why it's called LiveWire. With LiveWire, the engineers who developed that or took the standards that existed and added a little bit of timing secret sauce to that, they were able to get the latency in a typical radio installation down to under 3 milliseconds. And that's really critical. That's why folks have come to us at Axis and say, hey, why don't you guys just use CobraNet? Why don't you use EtherSound? Well, again, they're perfectly good technologies, but they're not designed for talking into a mic and hearing it live and hearing it back into your headphones, your earpiece. You've got to have that low latency. The other thing I want to mention is that Axia consoles are what are being used at Leo's TWiRT network, at the Brick TWiRT house, and before that at the cottage. Right there is a big honking console. That is the main console for doing most of the productions that they do at the TWiRT network. That is an Axia Element console. An Element can have anywhere from 2 faders up to 40 faders. That one has 18 faders. 18 faders on that console. That console, by the way, has motorized faders. So if they want to, they can set up a profile, which when they load the profile, even zooms the faders up to the levels that they need to be at. So it can be very automated. There's mic processing built into to the console for all the microphones. There's automatic mix minus that is built into the console. So every single one of those faders that needs to provide a back feed to a source, like what I'm hearing right now, I'm getting a mix minus in my headset. It's coming from the Axia console's automatic mix minus capability. Really cool. Folks ask us, how many mix minus buses does it have? How many do you need? They're all virtual. The other console that is at the Brick TWiRT house is the Radius console. This is a new small 8-fader console, and it's in Leo's personal studio. And, well, there it is. The Radius console is very inexpensive. In fact, it looks like I'm going to be able to afford to buy 2 of them for my radio stations in American Samoa. So Leo got one of these. It's all he needed, 8 faders in his personal studio. You can have, of course, they're profiles, so you can change the inputs at will. You can change the inputs on the fly if you need a fader to be one thing or versus whatever it was. You can store profiles in there. Each fader does have the ability to do a back feed, just like on the big Element console. So it's a really convenient thing to install. And I got to tell you, installing one of these consoles, the Element or the Radius, and I should say especially the Radius and its big brother, the IQ console, these are quick installs. Maybe your first one will take you a bit longer because you got to figure out, okay, what do I need to program? What do I need to configure? It's all done by Web GUI, by the way. You just browse into it, and it's got a web server in there. You just make selections and save it. But I tell you what, your second console, your third console that you install, really fast. On my console in Cleveland, Mississippi, we have a small Element console there at my radio station there. Honest to goodness, swear to God, 3.5 hours is how long it took to install that console. The wiring and the configuration on the air in 3.5 hours. It took 3.5 days to build the furniture, and run the phone lines and such. The console, really quick. So with the Radius advertising, it says, hey, take a break and install a radius. Well, that's not really too far from the truth. So check it out on the web. Go to axiaaudio.com. There is the front of the website. Unpack, Connect, and Showtime. That's the Radius console and its big brother, the IQ. Invite you to check that out, and we'd appreciate it very much if you would. All right, let's get back to our show. We're on our show right now, TWiRT 107. We're talking about grounding and RF, wiring audio in a high RF environment.
Real quick, Kirk, I have a console story for you as you were talking about the setup with the console. I put in, I acquired a used Audio Arts A50 console for my studio in my basement.
Oh, yeah.
So I'm putting it in a couple weeks ago, and I'm getting it all wired up, and I have it all running. Everything's working really well. And what do? I lean over to tweak something and spill my water right into it.
Oh!
After all this time, telling the DJs in the studio, no, watch the stuff around the console. What do? Spill water right into it. Fortunately, I pulled the plug right away and dried it all out, and it was fine. But all that time harping on people not to spill things. What do I do with the one I have sitting in my basement? Spill water into it. First day.
Oh, and the console was okay, right? After you dried it out,
it was fine. Yeah, I unplugged it and pulled out all the modules and let it dry overnight, and it was fine. And that's the key. Is you gotta kill power to it right away and let it dry. But it seems to be so far no ill effects from the whole event.
By the way, in the chat room, Web 3236 says bourbon is actually much worse on electronic equipment. I know. Yeah, water's usually not too bad as long as you get the power turned off. By the way, that does let me bring up one more really interesting thing. On a console, an audio console, the point of ingress for liquids is typically those slots where the faders are, right? Because there's a slot where this thing has to move back up and down, and then you go down below that inside the fader, typically a Penny and Giles brand or something. It's got a slot on the top of it too. Well, my brilliant friends and engineers at Axia found a fader that actually enters from the side. So if you spill something into the top of it, I'm not saying it's waterproof, but if you spill something in the top of it, it does not go into the fader. It goes around the fader, and because the tang that you move up and down actually is bent into kind of a C shape, and it goes into the side of the fader. Brilliant, just absolutely brilliant. Some Japanese company came up with that. And so, again, not saying it's waterproof, but it works pretty well. All right, back to keeping RF out of signals. We kind of covered this analog stuff, and, a lot of it, well, I've been accused of that being kind of a black magic. Well, there is an art to kind of understanding where the RF is the RF energy, the RF interference is getting into an audio system. There are engineers who have tried and true techniques. Some engineers will tell you ground everything at the racks. Other engineers will say ground everything at the source and the destination, and leave the ground unconnected at the punch blocks or at the racks. Well. And you know what? There's valid reasons for both things. I remember an Auditronics console brand, their console that no longer exists, but they were in Memphis, and I used to work with them a bit. They always said, never ground. They want you to ground at the console, ground the shield of the analog wires at the console, but that was a separate ground that had a capacitive connection to the main ground. Other console manufacturers told you don't ground the shield at the console. Make sure it's grounded back at the source. And this had to do with the source impedance was typically low, and the console input impedance was typically very high. And you wanted the RF to drain out of the shield back where the impedance was low. It was less likely to get into the audio at that point. Well, what I'm getting around to splaining is that in today's world, we have a lot less of this analog RF problem. We have a lot more AES audio and Ethernet IP audio, which blessings, can really solve RF problems to a large degree. So, Chris and Chris, why don't you guys talk for a little while about RF grounding and what's necessary about getting RF out of circuits where you've got AES digital audio. And I'm going to ask you guys to talk about that because I never worked at stations that did a lot of AES. We did very little AES audio. So you guys probably have a lot more experience with that than I do. So what's important with RF and AES?
I think I'll defer mostly to Chris for this because actually I'm with you. I actually haven't done a lot of grounding with digital yet, so I'm still kind of getting my head around it as well. So I believe Chris, you've done some, actually more than some digital wiring, so you probably have a little better insight to this.
Yeah. Well, the AES circuit designs in general use a lot of filtering, whether it be capacitive or inductive. Just by nature of the design of what they have to do, because the digital frequencies, as we know, they're very high frequencies and susceptible to any kind of noise. And what I've also found out is since we've moved into somewhat of a digital world, whether it be from IP or just AES audio in general, a lot of circuit design now requires, because the frequencies that these digital circuits operate at require by default heavy-duty RFI filtering. So 20 years ago, you buy a open reel machine, and the audio inputs and outputs were basically transformer coupled, if that, or DC coupled with capacitors and very little filtering because not much was going on around it. Now you've got equipment in environments with PCs running at 2 gigahertz and LAN connections running at 10 gigahertz or 1,000 gig, and you've got RF everywhere. So with AES, it's a digital stream, so any alien noise is enough to create havoc. Analog audio, as we know, is very forgiving. Digital audio is not forgiving at all. So with AES, by design, the circuits ins and outs are actually filtered very well. The hard part is making sure the cabling is done right. The source impedance, just don't use any cable. I mean, short distances, like 2 or 3 feet, you can get away with some shortcuts if you have to. But anything of consequence, you definitely want to do 110 ohms, and do it balanced, proper AES. If you do SPDIF, which is the consumer version of an AES signal, you do need to convert for impedances. It's a different impedance. So, there's some care and feeding required. But AES and RF interference don't go well at all. It would be the same as digital video and any kind of noise from, say, a hairdryer nearby and like a video camera. You get those little white specks, or in the case of digital video, dropouts, squares.
So one thing that so AES, at least in the radio broadcast world, we tend to use XLR connectors and have balanced audio wires, and typically that wire is shielded. And because it's balanced, unlike, by the way, in TV where they used unbalanced, they used 75 ohm unbalanced cable and BNC connectors for AES EBU audio. But in radio, we use this balanced circuitry. And I'm given to understand that the input circuit of most AES inputs consists of a transformer. Do I have that right? Is there a transformer on the input of AES circuits? Okay.
Yeah,
well,
there's a transformer.
Yeah. Well, a transformer is just an absolute godsend when it comes to getting rid of RF, unless the RF is really, really high level, because a transformer, by its very nature, only transfers from the primary side of the transformer to the secondary side of the transformer. All it transfers from one to the other is the differential voltage, the differential signal between the two conductors. So again, RF typically enters any wiring as common mode. It's common to both conductors in phase and amplitude at the same time, or it's on the shield. And so the transformer pretty much ignores anything that is common mode. Now, we also have electronic circuits that have pretty high common mode rejection, but a circuit like that still could be, even if it has great common mode rejection, the circuit itself, the whole circuit can be swamped with way too much RF. I mean, get ridiculous. Imagine putting, 1,000 watts of RF onto some little instrumentation amplifier input, and you're going to blow the thing up. There's also a point where it'll, end up passing a lot of RF through it. So a transformer, though, is just a terrific way to break to eliminate ground loops, if that's a problem, and to make sure that just the signal of interest gets from one side of the transformer to the other side of the transformer. So that said, that's also the beauty of using Ethernet to pass audio, because if I'm not mistaken, up to a 100 megabit per second connection, 100 base T Ethernet connection, there is also a transformer as part of, actually maybe two transformers, as part of the circuit of interfacing the two. Now, there may be other ways to get that done, through capacitors or other ways, but I know I've seen some tiny little transformers as part of an Ethernet connection. Now, I believe when you get up to the gigabit connection with Ethernet, they have to use all the conductors, and it's my understanding that you don't have the transformers anymore. There's some more direct connections there. So the thought is that perhaps gigabit Ethernet connections may not be as RF resistant in a high RF environment as 100 megabit connections are. There's other ways to get it done too. I mean, obviously there's fiber, which is a terrific thing because it doesn't care about RF whatsoever. The RF just passes right through that fiber and never gets on it. So, Chris, TAR, you are getting ready in your neck of the woods within the next, year or two. You're going to be putting in some new consoles, new audio, new wiring plant. You're going to be doing some digital stuff there. Do you anticipate, or do you have any idea what you're going to do to see about keeping away from RF problems there?
Yeah, actually, we're going to be breaking ground here in the spring, so it's coming sooner rather than later. My building now, my facility now, has a very well-designed audio ground system. We have at the rack points, we have a bus bar. We do kind of the star grounding where we have each studio is on a ground that's tied together. All the racks are grounded together. So I'm imagining that when we build the addition onto the facility for the studios, we'll just simply tie into the grounding system that already. We will have to put a lot of copper into the ceiling and the walls around the studios to keep the noise from coming through the walls. But I imagine with the racks and the audio to the studios, we'll be the ground system. Excellent. We're right outside of a 5,000 watt AM signal, and I don't have any noise on anything.
Hey, Chris Tobin, I would imagine that some of your experience with high RF environments has been when you put, in New York City, in a big city like that, you typically will have a backup studio, and it may very well be at the transmitter site.
Yes, absolutely. And we do practice all types of RF filtering and grounding and shielded twisted pair cable everywhere where you can go. And what's nice is with wiring, if you do twisted pair, shielded, the twists in the wire help to cancel out any interference. So your added protection could be some toroid filtering connections with RJ45 connectors or XLRs. But another place where there's a lot of RF that you wouldn't think so because it's not an AM site is at the upper floors of the Empire State Building where the FM, TV, and lots of two-way radio people transmit from. And
of course.
You can get interference up there like you wouldn't believe, and it's just the funniest thing because sometimes it's there and sometimes it's not.
Oh my God, I forgot about that. Now on the upper floors of the Empire State Building, you're a long ways from ground, Mother Earth ground. You're 100 stories up or 90 story, whatever it is up. What do you do? Does ground just become common? Are the transmitter facilities tied together in some way? Are they tied to the building structure? How do you deal with that?
Ground is pretty much tied to the building structure. In our case, the building is steel girders. It's not a lift slab construction like newer buildings. You can get a pretty decent ground connection, and because there's a master antenna system as well for the FMs and some of the television, a lot of the grounding is to the building, which seems to work. It proves interesting at times. But yeah, you think about it, you've got television transmitters, you've got FM transmitters, two-way radio transmitters of many types, and you have those specialized low-power TV transmitters up there. It's a challenge at times. If you're not careful, you can once in a while get some nice interference, strange-looking stuff, and listening.
Yeah, and all that RF from the Empire State Building itself and from other nearby buildings. And, of course, people have cell sites and two-way sites on buildings nearby. So I would imagine that could be quite a nightmare up there on the Empire State Building. Luckily, you don't have a lot of, I guess you don't have too much studio gear up there. It's typically audio processors and STL gear and things like that. You might have had some analog audio, but hopefully short runs in a controlled environment.
Oh, absolutely. But in today's equipment, most of the equipment today, it's well filtered. It's designed really well. And if you have interference issues or RFI on most standard installations, you've definitely done something wrong. If you're in a high RF environment and you're going to be in it, and you have a lot of microphones, stay away from condenser mics. Try and stick with dynamic, moving coil types, and that kind of stuff. But if you do it right, a lot of the stuff out of the box, you don't have to go too crazy. The interconnection is just good shielded wire. If you're going to do audio cables, you have a quad pair. There's various manufacturers of it, so you have 2 twists for each leg of the XLR shield, and then 2 twists for pin 2 and pin 3. So that in itself gives you a lot of commode rejection. The shielding adds another layer of protection, and if you properly terminate and keep everything clean, you're in great shape. You don't have to go too crazy with toroids or do anything funky.
Got you. Guys, there's actually a lot more that we could discuss on this, because there's there's the whole subject of how you might run grounding bars in a studio or in a rack room. I guess what brought a lot of this to mind was I was at a station a couple days ago here in Nashville that had fantastic copper bus bar ground system in the rack room, and to avoid creating ground loops, this bus bar was along the top of the racks, but it was insulated from the racks with high voltage insulators just to hold it sturdy in a good mechanical way and electrically away from that. Also, the AC power ground was tied into this station earth ground. They had been able to do that legally with approval from the electrical inspector. And what the result is a really good, superb quality ground that they can, when you tie anything into it, that you're not going to be adding any RF to your problem. You're going to be dumping the RF interference into this ground. And then this ground was very well tied into the transmitter building and the tower and the wires under the ground, the ground rods and the lightning rods and so forth, so that whether it was the local on-site AM transmitter that they rent space on their tower to, or whether it was one of their backup transmitters, which are pretty high power, like 10, 12,000 watt backup transmitters, they would be able to, they wouldn't have RF interference coming in because they had such a good infrastructure in the plant to tie things to. And a lot of their plant, a lot of it's still analog, but a lot more of it is AES digital, so it's less susceptible to the kind of RF interference that would plague us at some radio stations. Heck, I remember years ago I was doing some engineering, installing a console, and unfortunately it was a pretty inexpensive console. I like to call it a radio instead of a console, but it was the place where they chose to build the studio was a room in the radio station that literally was 6 feet from the AM tower. Why? I don't know why you design a radio station such that the AM tower isn't 60 feet from the building, or 160 feet, or 600 feet from the building. Why it had to be, why they had to locate the tower and the studio inches from each other is just beyond me. But you can imagine the level of RF in that room was pretty high. It was 1,000 watts, maybe it's 500 watt station. It was actually legal from an RF exposure point of view to be in that room, but not by much. And legal or not, it was tough to get a console to work in there at any kind of a reasonable way. Any more horror stories like this, I guess we're going to have to save for another episode, because we're about out of time. Chris Tarr, you got any last minute advices for us about keeping RF out of our desired audio?
Other than, the grounding issues and the toroids, no. The only other thing I would mention is if you've got an AM station and you do have a lot of RF around, check the grounding on your AM towers too. I do find too that there are some stations with bad antenna systems that cause a lot of RF in the near field, as opposed to a station that has a good ground system to it. So that may also be something you want to look at if there's a huge problem with RF in your facility.
Gotcha. Hey, Mr. Tobin, any last minute things you'd like to add to our conversation? He's muted.
And again, this microphone keeps muting itself. That's not good. Just make sure you have tight connections. If you're using XLR connectors, make sure they snap into place. And if you're doing shielded cable, make sure the shield is on both ends connected to the ground and to the connector itself, the shield of the connector. Other than that, just general practice and you should be in good shape.
Gotcha. All right. Well, folks, I hope we've given you a bit of an insight into RF grounding. There are some books and manuals written about grounding and having a good station ground. One of the ways that I learned about this subject and started to be able to take it seriously was actually from a manual or a supplement to the manual that came with a Nautel brand transmitter. The subject there was more about keeping lightning out of your transmitter and keeping it from blowing up. That kind of heavy-duty infrastructure for grounding is really helpful when you're trying to solve other grounding or other RF interference problems. But the good news is, hey, I really believe that we're in a better place. It's easier now to get rid of these problems than because of digital. Because of AES and Ethernet, it is a bit easier to get rid of this. I guess one more point about this. I was visiting WOWO, WOWO in Fort Wayne, Indiana, and they were putting in an IP audio system there, and we used on the longer runs, from the rack room out to each studio, rather than using copper twisted pair cable for the Ethernet runs, they used fiber. So they had no RF pickup whatsoever on those fiber runs, and then they'd have an Ethernet switch in each studio, and then a core switch, if you will, back in the central rack room. And so they're obviously all their long runs. They didn't have any antennas there. They had fiber runs, which don't act like antennas whatsoever. Hey guys, we've got to give away a prize. It's our weekly giveaway. We give away a license, a copy of Omnia AXE, which is software that runs on a PC as a service. It's good, reliable stuff. I like it. Runs at all my radio stations. And it does audio processing on your incoming audio, and then it will encode it as MP3, AAC, HEAAC V2, as our friend Greg Oganowski says, is the best thing out there to stream to listeners at reasonable bit rates. So we're going to give away an Omnia AXE license. And let's see, how about Mr. Tobin? I need a number between 1 and, let's say 18.
19. I'm sorry, 17.
17. I'm going to count backwards from the end. And all right, we have a winner. Oh my gosh, I know this guy. This could this could look like impropriety in a giveaway. But no, this was number 17 in the list here. Stephen Wilkinson of Hope 103.2. in Australia, with a 103.2. It's not the U.S. Hope 103.2. Stephen Wilkinson, congratulations. You are the winner of Omnia AXE. And Stephen, get in touch with me, and I will make sure you get your license and your download instructions. Hey, thanks to all of you who retweeted the announcement that the show was starting. We appreciate that very much, and we really have built a bigger base of listeners thanks to your efforts. And we've given away, I think, about 12, 15 copies or so of Omnia AXE. Oh, thanks for the kind words from Bogo Interactive about how much he's loving his Omnia AXE. Sure appreciate those kind words. All right, guys, we're going to wrap it up here. Our show, This Week in Radio Tech, has been brought to you by Axia Audio on the web at axiaaudio.com. Thanks very much to Burke back in Petaluma, California, for switching and our show and making us kind of look like reasonably intelligent people, correcting our mistakes and making us look all pretty. Burke, thank you. And thanks to Chris Tarr in Muckwonago, Wisconsin. Appreciate you, buddy.
Thanks for having me.
It's always good to be had. And thanks also to Chris Tobin from New York City. Thank you very much, Chris, for being with us.
Oh, you're welcome. It's my pleasure.
All right. Hope to see you guys not next week. We're off next week, but we'll see you the week after that. I've got some good guests coming along. I don't know if I should promote them or not, because we never know exactly which week they're going to make it on, but we do have some good guests coming up. Thank you for listening and participating in This Week in Radio Tech. We'll see you later. Bye.